Hello students, welcome to Go Vidya. Let us see the continuation of the questions in control systems. Now let us see the questions. The given question as follows. See, by a suitable choice of the scalar parameter k, the system shown in the figure given below can be made to oscillate continuously at a frequency of. That means what they are asking. So continuously the system is going to make oscillations by choosing the proper value of gain k. How to choose that? So first let us try to solve this question by using conventional method. Once we are comfortable with the conventional method, then we will see some shortcuts how to find out this, the frequency of oscillations continuously. So first of all, let us take the g of s, the given transfer function. G of s is equals to k by s into s plus 2 into s plus 8. This is g of s. And anyway, they haven't mentioned anything about the feedback, so it is a unity feedback. What is the characteristic equation of it? Can I say that? Or closed loop transfer function CLTF, or you can say closed loop transfer function k by, you multiply this everything s a cube, because this is s square into s a cube, plus 2s plus 8s, how much? 10s. So 10s square plus 8 2s are 16 into s plus k, because it is a negative unity feedback. Okay? So now what is they asking? Frequency of oscillations, because we know for the second order system we can directly find, but for the third order system, how to deal with that? Use RH criteria. Okay, so what is RH criteria indicating? First s cube, s square, s to the power of 1 and s to the power of 0. So if you observe very carefully, we have to first build the first two rows of the RH table for any characteristic equation. So what is the characteristic equation? The first coefficient s cube. S cube ka coefficient is how much? 1. S cube ka coefficient is 1. Then 16. Correct na? Now what else left? 10 and k. Right? Now we know that this point, how we are going to write at this value? So 10 into 16 na? 10 into 16 is 160. 1 into k minus k divided by what? 10. Do we have anything apart from this? 0. Right? Now you just simply calculate this. This value into this value minus 0. So this product only available. And also we have to divide with this number. So what else left? K only. K. Right? So now go back to the question. So as per the given question, what they said? System to be oscillate. Oscillate means the poles are lying on imaginary axis. In such case, we have to assume that oscillate, continuously oscillate. What is that? Oscillate continuously, which is also called what? Marginally stable. Very, very important. Marginally stable. What is the condition for marginally stable? You see here, there should be first of all no sign change, right? So for which value this is going to be, remember one thing, the k value should never be negative first of all. Okay, so it has to be greater than 0, right? So what I have to do, I have to equate the s power 1 row to 0. S power 1 row to 0. If I make it s power 1 row to 0, what is the value of k you will get? Simply the value of k is, if I equate it to 0, 160 minus k, then k is equal to 160. So you got finally, degrees nahi hai, 160. Now we have to find out the frequency of oscillations. Frequency of oscillations means for frequency of oscillations, for frequency of oscillations, always equate s square rho to 0. Okay, if I equate s square rho to 0, so what you will get? I have equated s square rho to 0. What exactly the s square rho? What exactly that s square rho? 10s square plus k is equals to 0. Right? 10s square plus k equals to 0. From that, s is equals to what? Plus or minus j root of k by 10. Correct? Why I got imaginary term? Because k is a negative, right? Minus k. So now what is the k value which we got? If you see, k value we got 160. Substitute that 160 here. Plus or minus j root of 160 by 10. How much this is? Plus or minus j. So root of 16 is 4. Now if you observe this, it is looks like a plus or minus j omega. So therefore can I say this 4 refers what? Omega. Therefore frequency of oscillations for this particular given transfer function is how much? 4. So 4 radians per second is the correct answer. Okay, but for the same question, the same characteristic equation, we can solve in another way. How? Let me take this s cube plus 10s square plus 16s plus k. Let me say method 2. Method 2. What is method 2? First take the characteristic equation. S cube plus 10s square plus 6s plus k. Correct only na? S square plus 10s square plus 16s plus k. This is what the characteristic equation, right? So whenever if we are talking about marginally stable, for marginally stable condition, for marginally stable condition, what is the relation for marginally stable condition? Always inner product must be outer product. Okay, inner product must be equal to outer product. What is the inner product? 10 into 16, and inner product is this, outer product is k. Therefore directly can I say k is equal to 160? K is equal to 160. Now frequency of oscillations omega, straight away we can write relation I am giving, root of constant divided by coefficient of s square. Constant divided by coefficient of s square. This everything is under root only. So as per this given question, you just take it. Constant value kitna? 160. And what is the coefficient of s square here? 10. So directly we can write the frequency of oscillations are 4 radians per second. This is applicable if you have only third order system. Okay. So this is how we are going to solve. Is that clear? What you need to do, only thing is for marginally stable condition, inner product must be equal to outer product. From that we are getting the constant gain k. So by using that constant gain k, by using this relation, we can calculate the frequency of oscillations. This is the method we are going to use to calculate the frequency of oscillations if it is more than the second order. And directly we can write it for third order. If it is beyond third order, fourth order, fifth order, sixth order, na, story is remains same. Like, but by using what? Not this shortcut, we can use this method. What is that? Yes, s power 1 row. First you have to make it 0, then we will get the k value. Then we will make it s square row to 0 to calculate the frequency of oscillations. I hope it is clear. Now let us go to the next question. Very, very important model. Just check it. Especially for TRANSCO GENCO, maximum you can expect the order of the given characteristic equation will be like max to max 4 only. Beyond that it is difficult because it is time consuming. Now let us see the number of roots in the left half of S plane. What is S plane actually? This is imaginary axis and this is real axis. Left half of S plane, how many roots are there? Strictly speaking, definitely we can say this system is unstable because it is satisfied the Hurwitz condition. What is Hurwitz condition? If you say that the system is stable, there are two conditions must and should satisfy Hurwitz conditions. If there is any sign change in the characteristic equation, that is the first thing. If there any term is missing in this characteristic equation, like for example s cube 4s square 6, but not they have not given s value, they have not given s value, then also we can say the system is definitely unstable, but we don't know how many poles are in right half of S plane or left half of S plane. Okay, and first and foremost thing we have to remember, RH criteria will give you the information only how many poles lying on right half of S plane or left half of S plane or imaginary, but it will not give you any information related to exact location of the root. Suppose if you say third order system, one pole lying on right hand side, two poles lying on left hand side, for example. So two poles may be lying here or here or here, it may be anywhere. They will not mention exact location of the poles. For that, what we have to do, like we need to identify like root locus, etc., etc. we are going to take. Okay, anyway, let us see this. S cube minus 4s square plus s plus 6. So let us take the Routh's table. What is that? S cube, s square, s power 1, s power 0. What is that values? 1, 1. Alternate terms, na? Alternate terms. Minus 4 and then 6. Now what is this value? Minus 4 into 1, minus 4, minus 4, 6 into 1, 6, minus 6, divided by minus 4, and anyway nothing is there, 0. And obviously, if you multiply these two and divide with this number, anyway you will get 6 here. Correct, na? So our objective is only to identify the number of poles lying on left half of S plane or roots lying on left half of S plane. You see clearly what is the sign of this? Positive. What is the sign of this? Negative. And what about the sign of this? You see here minus 10 by minus 4. Okay, whatever may be the value. Minus 10 by minus 4. But minus by minus is positive. So this is positive. And of course this is also positive. Now observe the sign changes from the first element. You see from here to here. Yes, one sign change is there. Here to here. Yes, another sign change is also there because it is changing from plus 1 to minus 1. It is changing from minus to plus. But is there any sign change from here to here? No. It is from plus to plus only. Therefore, how many sign changes are there? The number of sign changes is equals to how many? 2. If the number of sign changes are 2 means the number of poles lying on right half of S plane, which is nothing but the number of sign changes. So what is the actual order of the system? Actual order of the system is 3, na? 3. And out of the 2 sign changes are there. That means out of 3 roots, 2 roots are already lying on the right half of S plane. So that means it may be anywhere. Okay, let us say this is one root, this is one root. Out of 3, 2 roots lying on right half of S-spline and 1 root lying on left half of S-spline. As per the question, he is asking how many roots lying on left half of S-plane. How many? Only 1. Therefore, our option is A. Clear enough? But ultimately, it is very clear that poles are lying on right hand side. But how many we don't know. To understand that, yes, we have to use this RH criteria. Right? I hope it is clear. Now, let us see another question. Now, read the question. Consider the following statements. Routh-Hurwitz criterion gives absolute stability, as it is true. The number of roots lying on the right half of the S-plane, yes, it will give. The gain margin and phase margin, is it possible to calculate the gain margin and phase margin? No. So therefore, which option is correct? 1 and 2. Correct, na? It will give you just stability information only. How good it is stable. Whether it is a stable or marginally stable or imaginary stable or unstable, that information only it will give. But it will not give the gain margin and phase margin. Okay? Yeah. Simple question. Now let us see another question. Yeah. Look at this characteristic equation. The number of roots lying on left half of S-plane. Left half of S-plane. Let us see. What is the characteristic equation? S cube, S square, 7S3. No term is missing, no sign change. So we have to predict. So let us see this. Take the Routh's table. S cube, S square, S power 1, S power 0. So what are all those values? 1 and 7, 5 and 3. Now you do it. 5 7s are 35. 35 minus 3, 32. 32 divided by 5 na. And this is 0. Correct? 5 7s are 35 minus 3. So 32 divided by 5. In a way, whenever S power 2, S power 1, 0, you will find a square matrix. Type like this, square matrix type. You see, whenever the second element below, if you have a 0, straight away we can drop this here. Even if you calculate the same, this into this, minus 0 by this element, you will get this. Right only? 3. So did you find any sign changes? No, right? There is no sign changes at all. This is also positive, this is positive, this is positive, this is positive. If there is no sign changes, then we can say number of sign changes is equals to how many? Number of sign changes is equals to 0. What is the order of the system? Order of the system is 3. So no sign changes means no roots are lying on right half of S-plane. So all the roots are lying on left half of S-plane only. So therefore, how many are lying on left half of S-plane? 3. Correct, na? Let us solve this question in much more simpler way, because when you are going to attend any competitive examination, time constraint is very important. If you draw like this and if you solve like this, definitely it will take more time. For any third order system, method 2. Method 2. For any third order system, if you see here, if the inner product value, what is the inner product here? IP. If the inner product value is 35 and the outer product value is how much? 3. Follow very carefully. If inner product is greater than outer product, only for third order system. It is applicable for only third order system. If inner product is greater than outer product, then we can say system is stable. Absolutely stable. No doubt at all. If, for example, with red color I am indicating, if it is so less than, in such scenario we can say system is unstable. This information we can say. But we don't know for unstable case how many on right side, how many on left side. For unstable case, we cannot say directly by looking into the characteristic equation how many on right side, how many on left side, we cannot say for unstable case. But if you consider for the stable case, when I state a big statement called stable that indicates all the roots are lying on the left half of plane. There is no scope for even one root on right hand side. So therefore directly we can I think so within 1 or 2 steps we can, one step, less than 10 seconds you can easily do. You check the inner product, you check the outer product. Which is more? Yes, inner is more stable, inner is less unstable. If it is unstable, you have to do this because we have to know how many roots are lying on right hand side and left hand side. Okay na? So therefore answer is 3. Now let us see next question. Yeah. Now let us see the question. They have given this open loop transfer function. What is this open loop transfer function? G of s is equal to 1 minus s by s into s plus 2. The system with this transfer function is operated in a closed loop with unity feedback. They said simply unity feedback. They haven't mentioned whether it is a positive feedback or a negative feedback. So obviously what we are going to consider? It is negative feedback system only. Correct? So for the negative feedback system, what is a closed loop transfer function? We know that numerator will be as it is na. So denominator plus numerator, that is nothing but closed loop transfer function because of negative feedback. So can I write like this? S square plus 2s plus 1 minus s. Can I write like this? 1 minus s by s square plus s plus 1. Right? Now what we need to do, we have to check the closed loop system is stable or unstable or marginally stable or conditionally stable. First of all, there is no scope for conditional stable. Why? Because there is no term called k or a or bc, any variable. And one thing is very sure, there is no sign change because it is a second order system. For second order system, it is applicable, you can say directly. Hurwitz satisfied this condition. If it is a second order system, if there is no sign change, it is absolutely either stable or marginally stable, but it will be never unstable. So 2 options we have eliminated. So the answer can be either stable or marginally stable. Okay. So whether it is stable or marginally stable, how we are going to say? Yes. Tell me s square plus s plus 1. What is the roots of this characteristic equation? You can find or directly can write it as stable also, but for you I'll do minus 1 plus or minus root of 1 minus 4 by 2 minus 1 plus or minus 3 means 3j by 2. So if you observe very carefully, what sort of roots we got? Yes, complex roots. Whenever if you are getting complex roots, we can directly say that it can be, yes, not it can be, you can say directly it is a marginally stable. Suppose if the roots which you are getting as a real roots, we can say stable. So as of now, this is what? Marginally stable. Because the roots of this characteristic equation, we are giving what? Imaginary roots. So because of this, we can say the system is marginally stable. Okay. Now, let us see another question. What is the transfer function they have given? Open loop, that is the open loop transfer function. Obviously operated with unity feedback system. What is a closed loop transfer function? K by s square t plus s plus k na, because we are going to just add numerator and denominator, that's it. So now let us write this is into standard form. K by t, that means I am taking common t, which is nothing but s square plus s by t plus k by t. This is what our closed loop transfer function is, right? Now, what is the system condition this now? If you see the previous question and this question, you will clearly understand. Previous question, there is no concept of, or there is no term involved. There is no term involved as a k or t or a or b. So directly we can eliminate the condition stable option. But if you see very clearly here, there is an option called k by t. There is an option called 1 by t. So that means the stability of this system is decided by whom? This fellow and this constant fellow. If this constant value, they haven't mentioned anything anything about the k and t values. If they are if they have mentioned that where k and t are the positive real numbers, for example, if they have mentioned k and t are positive real numbers, so that means this is positive, this is positive, this is positive, this is positive, then what will happen? No sign change. Straight away we can say that system stable. But here it is obviously depending upon the value of k and t. So from this we can say the system is conditionally stable. So conditional stable means, remember one thing, it is always depends on a particular variable given in the transfer function. It may be the gain k, or it may be like this time constant t, depending upon the circuit things we can say, or transfer function. Okay, so this is about what? The closed loop unity feedback system is conditionally stable because these values are depending upon the stability of the system is depending upon k and t values. Okay.